So I sent out an email about the logistics of our final exam. So as we've done for the last few years, we'll have 20 multiple choice questions and 3 long answer questions. Now, the percentage breakdown is given, the point breakdown is given here too, but so percentage wise, the 20 multiple choice questions will make up 1/4 of your final exam grade. And then each of the long answer problems will also make up 1/4 of your final exam grade. So all of that is the same as if we were, still doing this in Rochester, right? So if we were doing this in person, none of that would be different. I guess the different part is that we will be delivering our exam virtually. And as we've sort of hinted at for the last couple of classes, I can now confirm that we'll do that in 2 separate parts. So we're going to do the multiple choice questions over the weekend, and then we'll do the long answer problems in the time that's been allotted to us by SIS. So just, maybe before we get into the details, I guess the rationale for that is that we're hoping that this provides students with a little bit more flexibility. You'll be able to do the multiple choice questions kind of on your own time. So you'll be able to choose your own time slot in that 39-hour window. And then I think it gives us more time for the written part of the final exam, so we don't feel crunched with kind of downloading the exam, accessing it, and then uploading it at the end. So that's kind of the goal here. The multiple choice, the quiz will open 9 a.m. on Saturday. That's the 25th, so that's this Saturday. And it will stay open until midnight on the 26th. So there will be a 39-hour window where the multiple choice questions are open. Now, our thought for leaving it open for that long is that you can find a time that works for you, because this time hasn't been sort of scheduled. It wasn't on anyone's calendar before, right? So we're giving you a wide window. We're not expecting that this will take you 39 hours to complete. We have the final exam now. I did it yesterday. Granted, I'm teaching the class, but the multiple choice problems took me 15 minutes to complete. So I think that usually, the multiplier would be sort of, 2 or 3 times, right? So we would normally in an exam be allotting about 60 minutes for you to do these multiple choice questions. So I think there's enough time to do that. The nice thing about the multiple choice questions is that there won't be anything for you to hand in. So we will make the normal question sheet available, and then we'll also have the questions in a quiz on my courses. So just like when you're doing your quizzes, you'll select these things and then submit the quiz. So we'll be able to see how long you have the quiz open for and how long you're working at it. Like I said, we expect that a student without accommodations would finish this exam in less than 120 minutes or 2 hours. And we'd kind of scale that expectation for people with accessibility requirements. So the other part of the exam, as I scroll down here, is the long answer part of the exam. So this will happen, unless you have a conflict, this will happen as scheduled on SIS. So we're scheduled on April 30th from 4:15 to 6:45 Eastern Standard Time. So that's 2.5 hours. And because we only have the long answer portion to do in this time, we sort of expect in a sort of normal exam setting that those 3 problems would take 90 minutes to complete. So instead here you have 2.5 hours. And that's because we acknowledge that it will be difficult to access the exam, or at least different to access the exam, to then scan your work and then submit it. So we will keep the Dropbox open till 7:15. So we have a grace period on top of that 2.5 hours, so that it's 3 hours. And then if you have conflicts, or if you have approved accommodations from the university, then we'll sort of adjust that window as is appropriate in individual cases. So I think the last part of this, which I don't know, we end up talking about this a lot in things like faculty meetings. I think that there's a subset of people who are very worried about sort of the academic integrity of these online exams. In heat, I was going to say we're going to treat you like adults, but I think we're going to treat you like engineers, in that we're going to expect that you sort of approach this task with integrity. And I honestly believe that that's what people will do. So I think everyone knows what cheating looks like. And I think that, I don't know, I guess I have faith in you that you'll sort of approach this task honestly. Does anybody have any questions about the exams before we move on to the lecture material for today? So I think everyone who notified me of a conflict, I believe I contacted everyone. If you have a conflict and you haven't been contacted about heat, please let me know. If you contacted Brittany and not me, then I think she has set up an alternate exam time schedule on Friday for people with conflicts. So if you feel like you have a conflict and no resolution, please contact me as soon as possible. Thanks. Okay, so on to the sort of material for today. Whoops. So first, again, I'd like to sort of acknowledge and thank the people who have filled out the SMART evaluations form. We're up to about 34%, so more than a third of a class. I'm very grateful for the feedback that people have provided. I haven't got a chance to see it yet, obviously, but I think it's going to be important for us moving forward. I mean, again, we all hope that we'll be in the classroom in September, but the reality is we don't know, and I think your feedback on how the class has gone is very important. So thank you for filling this out. Appreciate it. So as we said, this is kind of what our calendar looks like moving forward. So just in sort of pictorial form, what we just talked about, we'll run the multiple choice portion of the exam from 9 a.m. on Saturday to midnight on the 26th. And then we'll have the written part, the long answer part of the exam on the 30th from 4:15 to 6:45. And we will keep the Dropbox open until 7:15. If for some reason you can't submit before 7:15, please try to contact us via email, or maybe I'll set up, I'll provide a text number that people can text as well. And then if internet goes down, then there's still a way to sort of get a hold of us. Now the focus for today will be, as you know, we have 3 review exams available online. So we're going to go over the second review exam. So this exam is from the second module, I think from 2015. This is an exam that they would have written in class. So the second module, if you remember, is kind of thinking about the heat diffusion equation, or conduction, sort of in 3 dimensions and also in time. So that's sort of the focus of this exam. So the first question in the multiple choice: which of the following terms is best defined by the ratio of the internal thermal resistance of a solid to the surface convective thermal resistance? So this is important when we're trying to figure out if something is a lumped system or not. We're trying to see which is the limiting resistance. Is it how heat or how temperature propagates through the material, or how heat leaves the system? So this is where we're looking for the BO number. And as we know, if the BO number is low, then we can apply a lumped capacitance methodology. Part 2, which of the following statements is the best definition for the heat diffusion equation? So I won't read all of these to you, but I've kind of underlined. So first I wrote the heat diffusion equation down, right? So this is on your exam, your equation sheet for the exam. So you'll be able to find it there. If you haven't looked at that sheet yet, I really encourage you to do the studying you're going to do for the exam using that sheet. So as I said, I did our exam yesterday, and because I haven't used that sheet all that often, I did find myself spending time hunting for equations on there. And if I was more familiar with that sheet, I think my experience would have gone even a little bit faster than it did. So here, I'm trying to physically understand what this equation means, right? So I'm not going to read all these to you, but I'm going to underline what I think are sort of the important differences in these answers. So part B talks about thermal energy storage in the surface, right? So one of the things that we know about heat transfer is if we have a controlled surface, we can't store any energy in there because there's no mass. So we know that energy storage term is not talking about what's going on in a surface. It's got to be talking about what's going on in a volume so that there's mass inside of it. Part C looks mostly good, but it talks about the maximum rate of energy transfer by conduction. And this equation doesn't tell us anything about minimums or maximums. We're not sort of taking a derivative here to do some kind of optimization sort of analysis. So this part is incorrect in C. It's not the max rate of energy transfer by conduction. Here, this one's a little tricky because D looks pretty good, but here it talks about the rate of change of thermal energy removed from the unit volume, right? So this is a sign argument. So here, because this is a positive value down here, as the temperature goes up, this term also goes up. So this is talking about energy stored and not energy removed. So if there was a negative sign in front of this term, then it would be energy removed from a unit volume. So D is incorrect. Part E also looks pretty good, but it's got this and convection going in here, and nothing in this equation talks about convection. The only time convection comes into our analysis here is when we're applying boundary conditions, but it's not. This is talking about what's going on inside the solid. So there's no convection inside of our solid. So it's not E. And basically by process of elimination here, we're left with A, the net rate of energy transfer by conduction into a volume at any point in a stationary medium, plus the volumetric rate of thermal energy generation must be equal to the rate of change of thermal energy stored within the unit volume. So these first three terms are talking about conduction in any direction, any of our three principal directions. Q triple prime or Q dot is energy generation per unit volume. And this term here is talking about energy stored within our volume. Question 3 asks us which of the following is not an assumption made when using the semi-infinite model. So the initial temperature is uniform. We need to assume that the temperature in our material, or our steak, for example, if we're searing it, starts at some uniform temperature, that the properties are constant. We can't really do any of these analyses that we talk about if the properties are variable. The Fourier number is greater than 0.2. Now remember that the Fourier number is a dimensionless time. In this semi-infinite model, this is when we're searing our steak, so we only want it to happen really quick, right? So it happens at low times. 0.2 is the cutoff for the Fourier number, but when we want a semi-infinite analysis, we want the Fourier number to be lower than 0.2, right? Hopefully we remember this from our case study, right? So C does not look that good. And D says heat has not propagated deeply into the material. So that's true, right? So we can't apply a symmetry condition at the center of our material or at some sort of insulated boundary condition because the penetration depth hasn't reached that symmetry line yet. So it's not really the right boundary condition to apply. So here the answer for C, which is not an assumption that we make, is that the Fourier number is greater than 0.2. Because for this type of analysis, we need the Fourier number to be lower than 0.2. Question 4 asks us, which of the following cases would you most likely use the semi-infinite model approach? The baking of a potato in a convection oven, The first couple of seconds of the cooling of a hot steel plate when exposed to a cool water jet, the heating of a thin copper wire placed in a high temperature furnace, the entire cooling of a ball bearing in air, and the cooling of a cup of coffee. So here I think, again, because we're talking about the semi-infinite solution being for the very beginning of the analysis, right? So the center of the, in this case, steel plate doesn't know that it's being cooled, right? So I think B is the best answer here. So now we're asked to consider a pipe that the length is much larger than the radius. So when you see this idea that the material we're interested in is much larger in one direction than another direction, then what that's telling us is it's 1D conduction in the small dimension. So here, the length is much bigger than r squared, right? So basically, we're not worried about the edge effects. So that's shown here in the right. And we're given an initial temperature, and it's suddenly exposed to a cold fluid on the outside and a hot fluid on the inside. Assuming constant and isothermal properties, what is the simplified version of the heat diffusion equation? So here, from the notes, although in the exam, you'll look on your exam sheet and you'll look for the heat diffusion equation for cylindrical coordinates, right? Now, when L is much bigger than 2, actually, I think the first thing that I do, right? So here, you might not see it. So we're saying that the properties are isothermal and uniform, right? Or they're constant and isothermal, right? So they're not changing. So I can take the K's out of all of these terms, right? So I have the same K in all my directions, and it's not changing with temperature. So I can pull it out of my differential terms and divide the whole equation by K, right? So that's what I did with this first simplification. The second thing is that we have 1D conduction. So we're only worried about conduction in the radial direction. There's no heat generation. It doesn't talk about generating heat anywhere in my problem, so I've eliminated that. And then I recognize the definition of alpha is K over rho Cp. So this term here, this constant in front of my transient term, is 1 over alpha. So when I do all this simplification, I realize that A is the same as this simplified equation that I have here. The next, we're still talking about the same case. It says, which of the following is the best pair of boundary conditions? So when you see this kind of equation, I always really force myself. This is one of those like spidey sense kind of things. I force myself to slow down when it's asking me about these boundary conditions because it's really, really easy. Maybe you're better at this than I am, but it's really easy to mess up the signs here. So I know signs are going to be important. So first I think about, okay, what do my different boundary conditions look like? And in this case, I have a hot fluid running through the center of my pipe and a cold fluid coming cross flow over the side of my pipe. So I have convection on the inside and the outside boundaries, right? So my convection conditions look like this, where on the left-hand side, I'm equating the conduction. This is actually for a wall and not for a cylinder, but it looks similar, right? So here, right, I have conduction on the left-hand side being equal to convection on the right-hand side. So I know right away that it can't be A, because A has at R1, it says that there is no heat transfer there. And that's just not the case, right? So we know that heat is coming in at that inside boundary. So A is incorrect. On its face, as I'm looking at them, all of these, the rest of these boundary conditions look okay, right? They're all convection boundary conditions. So I got to go through them and find out what's going on here. So when I do this, I try to remember, okay, where's the hot temperature and where's the cold temperature? So in this case, the hot temperature is going to be at the inside and the cold temperature is on the outside. So as R increases here, right? So as I move from the center of my pipe out, or the inside wall of my pipe out to the outside wall of my pipe, I'm cooling down, right? So that means that as R is increasing, T is decreasing. So my derivative, dt by dr, must be negative. It's less than 0, right? This is true at the inside wall, and it's true at the outside wall because there's no other source of heat in this problem. So both of these derivatives, dt by dr, at the inside wall and the outside wall, both need to be negative. So now I'm going to go through options B to E and look at the signs and make sure that the sign on the left-hand side of all these boundary conditions equals the side on the right-hand side of all these boundary conditions. So in the first one, I know that dt by dr is negative, and it's multiplied by a negative. So I have a positive side on the left-hand side of my equation, a positive sign. And now T infinity 1 minus TR1, right? So T infinity 1 is bigger, right? It's hotter in the hot fluid than at the surface because there's some resistance there. So this is positive too, right? This delta T is positive. So this B, the first part of B looks good, right? It's positive and positive, right? But the second part of B, it's positive still on the left-hand side, but it's saying T infinity 2 minus TR2, but I know as my radius is increasing, my temperature is decreasing, but the surface of the outside surface of the pipe is still hotter than T infinity 2, right? That's the cold fluid that's being used to cool this pipe down. So T infinity 2 is lower than TR2, so that's a negative sign on the right-hand side of my second boundary condition. So it can't be this one. I do the same thing. The first boundary condition is the same, so it's positive equals positive. And the second boundary condition flips my delta T around, so it's now positive equals a positive. So if you were going quickly, you might just stop at C. But sometimes I don't trust myself, so I'm going to look through the rest of them as well. Right? So here, again, I have a negative time times this derivative, so it's positive, right? The negative times the negative. But now this, TR1 minus T infinity 1, so this temperature is colder than that one, so this H times delta T here is negative. So a positive can't equal a negative. So this one, D, I can eliminate. And E, right? So again, well, I guess not again. So here, there's not this negative K. So this is negative on the left-hand side of my first boundary condition, but positive on the right-hand side. So I know that this one is also incorrect. So I've gone through all my signs here. So I slowed down and I took the time and I picked the one where all the signs were correct. So this is, I think, what you need to do for these kinds of equations, because at least for me, if I just look at them quickly, it's really easy to think that B through E are all almost the same. So we got to check the signs. I think that's what we do. Anytime we're applying a boundary condition, make sure your signs are correct. It's not just a matter of saying, oh, it's H times delta T, but what does that delta T have to be to make the sign equal to negative K times the first derivative of temperature with position? Question 7. For a transient problem that involves a thin, highly conductive wire subjected to a gentle breeze, which of the following would be the most appropriate model to use? So these are transient models, right? So we'd think about this transient flowchart, hopefully, right? So here I know that I can see if it's lumped by looking at the BO number. I don't have numbers here, so I can't calculate the BO number, but I can look at the form of this equation, right? So it's H times L over K. So here, L is going to be some characteristic length, right? Volume divided by area. But it tells me that it's thin, right? So it's thin. The characteristic dimension is probably small, right? It also tells me that it's a gentle breeze. So that tells me that H is probably somewhat small, right? And it tells me that it's highly conductive. So K is probably really big. So the two terms in my numerator are pretty small, and the term in my denominator is pretty big. So I'm going to assume that my BO number is probably low. So I think, I can't know for sure because I don't have the math, right? But I think the BO number is probably low. So there's nothing that we looked at called the BO number method. It's called the lumped capacitance method, but there might be some temptation to pick D because we're looking at the BO number, but that's not the case. So it's called a lumped capacitance analysis. This is a bit of one of those engineering decoder ring kind of questions. So here we would expect the BO number to be fairly low. So I think that this is a lumped capacitance problem. That's what I would pick here, and it is the right answer. So that's good, right? So when I did do this exam myself yesterday, I didn't look at the solution. So it's always kind of like, oh, you know, did we mess up the questions that we're asking, right? So in this case, the answer is correct. All the answers that I'm showing you here are correct. Consider a 5 diameter ceramic ball, we're given K and alpha, that will be removed from a furnace and exposed to a breeze at room temperature, where the convection coefficient is 30 watts per meter squared Kelvin. If somebody wants to approximate what the surface temperature would be after 4 minutes of exposure to room temperature air, what model is best used for the analysis? So now we actually can use our flowchart because we can find values for these things, right? Again, we know it's not the BO number method because there's no such thing. Well, we can calculate our BO number. We have a heat transfer coefficient. So the effective heat transfer coefficient is the heat transfer coefficient because there's only one resistor. I know that L is volume divided by area. So that I've shown this here. I simplified it a little bit already. Oh, this should be the pi r cubed should be in the numerator here, right? This should be 4/3 pi r cubed, but the pi r cubed should be in the numerator. So, but this, the answer is right. So then we get h r over 3 divided by k. So I can put that in. I work it out. I see the BO number is 0.17, right? And it's only lumped if the BO number is less than 0.1, right? So this is not a lumped capacitance analysis. So now I got to find out, I go to the next piece on my flow chart, right? Does heat conduct faster than it's stored? So I got to check the Fourier number. So Fourier number is alpha T divided by LC squared. So for, this is a sphere, right? Or a ball. LC is always going to be the length from my surface to the place where I've applied either a symmetry condition or an insulated condition. For a sphere or a cylinder, it's going to be the center of that sphere or cylinder. For a wall that's symmetric, it would be the half width of the wall. So here LC is R. So I have enough information to calculate the Fourier number, and I see it's pretty big, right? So it's much bigger than 0.2, which is my cutoff. So here it is a first term or a single term approximate solution. So I got an answer for question 8. Question 9 says, consider a 20 centimeter diameter titanium sphere, initially at 600 degrees Kelvin, presumably everywhere, right? We're given some properties. It's being cooled on all sides by water at a particular temperature with some properties, where the convective coefficient is given. How long does it take for the center of the sphere to cool down to 350 degrees Kelvin when the Fourier number is 0.53? So when I was doing this problem, when I was setting up these notes, I was like, oh man, this is going to be a lot of work because I have to go through and do the whole first term approximate solution, right? It has to be first term approximation if it's not lumped anyway, because the center has changed temperature, right? Kind of a lot, right? It was at 600 degrees and the center's now gone to 350. So it knows it's being cooled at the center. So it's first term approximation, or at least it's not semi-infinite. But then I realized, oh, the Fourier number is 0.53, and it's only asking me for the time. So if I know the Fourier number and I know the properties, I can just calculate the time. I don't have to do any kind of analysis other than just know the definition of the Fourier number. Now, the problem's a little tricky. It gives us a lot of red herring information because it's really trying to give you the opportunity to demonstrate that you know when you're doing this, you need to use the properties inside the material. So here, alpha is equal to K over rho Cp, right? So I calculated this out, right, using the properties of my titanium sphere, and I got a value, right? So I know alpha now. R is given, right? And so is the Fourier number. So I can just put this in, and I get 727 seconds, which is not on the list. Although if I wasn't worried about my units, I might look over here and pick, if I was just being quick, I might pick 726 minutes, right? Which is very different than 727 seconds. So I have to realize my units are in seconds, where all of these answers are in minutes. So I divide by 60, and I see that the answer should be A, 12 minutes. So we move on to the last multiple choice question. You bought a Hershey's chocolate bar to share with your heat transfer professor, which was very kind of you, right? But you forgot that you put it on top of your car's insulated roof as you were getting out on a very cold and cloudy Rochester day. By the time you remembered and went out to get it, 30 minutes had gone by. If the bar was initially at 20 degrees Celsius and cools uniformly, how cold was the Hershey bar after 30 minutes? Assume the bar has given dimensions and the following properties. And we're going to neglect edge effects, radiation, and thermal resistance between the wrapper and the chocolate bar. So here, I'm going to say that it's lumped. I could calculate the PO number, but it tells me that it cools uniformly. So that means I can do a lumped analysis. So the nice thing about these analyses, first term approximation is the same, is that we don't have to go through all the work of deriving an equation because we're kind of standing on the shoulders of giants, right? People have done this already, so we know what the answer looks like. But I don't know tau yet. I look on my equation sheet and find the definition for tau, right, which is my time constant. I know these values, so I plug them in, and I see that my time constant, again, I really got to be careful of my units here. And it's tricky because if I just look at the units in this equation, it doesn't look like I have seconds here, right? Except that watts is joules over seconds. So the joules in here is going to cancel out with the joules over here. And in the denominator, I'm going to be left with 1 over seconds. So then when I multiply that back up, I get 1800 seconds. So I got to always watch my units, right? And in this case, it's 1800 seconds that have gone by. So my exponent in my exponential term is -1. Now, one of the things I always do if I mess up these kind of problems is I forget that this exponent is supposed to be negative. So really make sure you check those signs, because I end up a lot of times I'm calculating these things individually and I forget to put the sign back in. So it's one of the things with exams. Usually if I messed up on an exam, at least often, it was little clerical things like that. And then I'd get my test back. I mean, you never got exams back, but when I got my test back, I'd be like, oh, what a stupid mistake to make, right? Only human, I guess, right? So here we know T infinity, we know theta naught, right? So that's my initial temperature difference, and I know e to the -1. So I work this out and I get 13.7 degrees. So the best answer here is 14 degrees Celsius. So that's it for the multiple choice questions. Does anybody have questions about these multiple choice problems we went through? Okay, we will move on to the first long answer problem. Again, written by Dr. Charlou. You can tell because it's a Star Wars question. So your team, apparently we're on the wrong side here, right? Our team is developing the ITO interrogation droid to get Princess Leia to divulge the location of the rebel base. The spherical droid, with a radius r and effective thermal conductivity k, generates volumetric heat, q dot, in ambient air having bulk temperature, T infinity, and convective heat transfer coefficient, h. Your job is to make sure it's designed to Darth Vader's specifications. Part A asks us to derive one algebraic expression in terms of these key parameters, which describes the temperature profile within the entire droid. And it's nice here, it reminds us how to calculate the volume of a sphere and the area of a sphere. Part B tells us that Darth Vader requires that the temperatures within the droid remain below 75 degrees Celsius, and we're asked to calculate the hottest temperature in the droid and determine if Vader will be pleased with the design. and then we're given a set of values. So we got to list our assumptions and justify or list and justify our assumptions and show our work. Here we're going to say we're looking at the steady state temperature, so we're interested in the operating temperature, constant and isothermal material properties, 1D conduction radially, uniform convection, and negligible radiation. So we're going to say that the heat loss from convection is much bigger than the heat loss from radiation. So now we have to derive an algebraic expression, right? And a lot of times I think sometimes students get intimidated by these kind of questions, but professors kind of like them because this is kind of like start from the equation and show me all your assumptions, cancel things out, and show me where you get your equation from. So this is heat conduction in a sphere. And these equations in spheres are always a little bit ugly because we have two different angles that we're interested in. But the good news is that we're talking about 1D conduction, right? So the theta term and the phi term are going to go away, right? So we're only interested in the transfer of heat radially. We're going to say that this is at steady state, so the energy storage term drops out. We're also going to say that K is constant, so I took K out of the derivative term here, right? So I moved it over here. I also dropped the subscript because there's only one K in this problem. It's not different in the radial and the azimuthal directions, right? So K comes out, right? And then we get this equation, right? So that's this equation here, but we want the temperature profile. So I know I'm going to have to do a little bit of calculus here. So first I want to use the method of separation of variables. So I want to get all my R terms that I can over to the right-hand side of the equation. So I multiply both sides of the equation by R squared over K. So this term drops out on the left, right? And then I get this term, which is basically a constant multiplied by R squared. So now this is a second order differential equation, right? So I got to integrate twice. So the first time I do this, right, I get rid of this part, right, the d by dr out here because I've integrated, right? And then I have to integrate that q dot over the negative q dot over k term, right? So that's times r squared. So now this becomes r cubed. I had to divide by 3, and I had to add some constant of integration over here. Now, again, I want to get rid of all the r terms that I can on the left and put them on the right. So I divide both sides of my equation by r squared. So I get dt by dr is equal to some term that's to the power of r to the 1, right? And then another term that's multiplied by r to the minus 2. I'm going to integrate again, right? So now I add 1 to the exponent of r, right? And now I had to divide by, in this case, 2, right? Because this was a 3 over there. So I divide it by 2. I get a 6 on the bottom, right? I add 1 to my exponent here, which was r to the negative 2. So plus 1 is r to the negative 1. And then this becomes negative because I got to multiply by that negative 1. And then I have some other constant, right? So we're on the road, right? So now we have an equation for temperature, but it's not specific to this problem yet because we haven't applied boundary conditions. So my first boundary condition is that my sphere is symmetric. So that means that dt by dr at the center of my sphere is 0. My second boundary condition, there's two different options that I can take. I'm going to recommend to you when you have these two options. So we can say that there's some constant surface temperature on the outside. I don't know what that surface temperature is yet, but it is some constant temperature. And the nice thing about doing this is that you see my first boundary condition applies to the first derivative of temperature, and my second boundary condition applies to the temperature as a function of r, right? So I like to have boundary conditions that apply to different equations here. But it's also true that I could apply a boundary condition on the edge of the droid because it told me that the conduction on the outside is equal to the convection, right? So the conduction going into the outside surface is equal to the convection going away from the outside surface. So here I just got to make sure that my signs are correct, right? But I'm going to show you that, well, I think in the solutions, I think they go through this second boundary term. What's going to happen here is just from this equation, you're going to find TS, and then you're going to have to apply basically my second boundary condition anyway. So I'm going to encourage you, when you have a choice like this, to apply that second boundary condition as just the temperature at the edge is whatever that temperature is, even though you don't know it yet. So when we apply our first boundary condition, if R is equal to 0, then we need C1 to be equal to 0. Or if the derivative at the center is 0, then we need C1 to be 0. So we need that term to go away, right? So we're going to cancel that term out, right? So now our equations are a little bit more simplified here, right? And the second boundary condition I'm going to say is that T at R is equal to big R, so at the edge of our sphere, is equal to some constant surface temperature. So if I do that, right, then I get this equation. So I take this equation and I plug in big R instead of little r. And that's just going to be equal to my surface temperature. I don't know what it is, but it only asked me for a symbolic solution anyway. So now from this equation up here, I can isolate C2, and I get an expression for C2. That's a function now of big R. So now I take C2, this expression, and plug it back into here, and I get a temperature profile for the whole droid, right? So if I put this in, I see that I can factor out this Q dot over 6K, and it's positive big R squared minus little r squared. And then that's going to be plus the temperature at the surface. So this kind of makes sense. This is telling me first that the biggest temperature, I think the biggest temperature should be at the middle, right? Because I'm generating heat and there's no more heat that can go to the middle, so it has to go out, right? So when little r is equal to 0, I'm going to get the biggest value here because this term is going to be positive. And then I'm adding TS, right? So I feel like I got my signs right here. And then as R goes to the edge, right? So as R becomes big R, the whole first term goes away and I'm just left with TS. So I feel pretty good about this equation, right? I can't prove that it's right, but I also can't prove that it's wrong, and that's pretty good. So now I got to see if Vader is satisfied. So I want to see if the temperature at the center of the droid, or the maximum temperature, remains below 75 degrees. Right? So I know that the maximum temperature has got to be at the center of the droid because I put a symmetry condition there. So it's either got to be the maximum temperature or the minimum temperature. But the outside's being cooled, so that's where the lowest temperature in the droid's going to be. So the inside has got to be where the hottest temperature is. So I don't know TS. That's my problem here. Otherwise, I could just plug in R is equal to 0 and find the answer here. So I can find TS from the first law. So if I did the other boundary condition, the order would be switched. So if I applied the alternate version of the second boundary condition here, the convection boundary condition we talked about, what would happen is I would find a value for TS first, and then I would use that value to find what my equation looked like, right? So the order is a little different. But I can find TS without even using the heat differential equation because I can just think about this as the same kind of problem we would ask in Module 1, right? So I find a nice picture of my droid, right? I apply a control volume, so the droid is inside the control volume, right? Except maybe some of the pointy bits, right? And I can just use my first law. Right? So this is, fits in with our, whenever you don't know what to do, try the first law, right? So we know it's at steady state. So the energy storage term goes to 0. There's no energy entering my system, but there is energy leaving my system, and the droid is generating heat. I mean, it's got to generate a bunch of heat, right? It's floating, right? So it's got to be doing a lot of work in there, right? So the amount of heat that it's generating is going to be Q dot, which is the volumetric heat generation, multiplied by the volume. And that's going to be equal to all the heat that convects away from the surface. So that's HA times delta T. So here I know that the volume is 4/3 pi r cubed, and the area is 4 pi r squared. So I sub that in, right? And instead of carrying this all through, I can simplify this equation. So I can isolate for the temperature on the surface, which is going to be T infinity plus Q dot times R over 3H. I feel pretty good about this equation too, because I know that the surface temperature, right, because this is generating heat, the surface temperature should be bigger than T infinity, and all of these terms are positive. So I should get a number that's bigger than T infinity anyway, right? Which is, I know that that's how it should be. So again, I'm not proving that I'm right here, but I can't show that I'm wrong. So I have some values here. I plug these in, and I find that the surface temperature is 70 degrees. And that's pretty good because I know that Vader wants the whole thing under 75 degrees. So at least the surface is under 75 degrees, right? So that's good. I haven't failed Vader's specifications yet, right? So now I got to go back to my equation, and I know that the maximum temperature is going to be at R, little r, is equal to 0. So I plug that in here, and my first term just becomes Q dot over 6K times big R squared. So I work this out, right? I put these numbers into my calculator, and I see that the maximum temperature at the center of the droid is 77.5 degrees, right? And Vader asked, he wanted the whole thing under 75 degrees, right? So 77.5 is bigger than 75. So Vader's going to be upset, right? So we didn't sort of pass the specifications. Does anybody have questions about how we approached this first long answer problem here?
I do have a question.
Yep.
So I was following along with the process, but I just have a question. Those boundary conditions, do we have to memorize? Like, because then, I mean,
do you have to? So the boundary conditions are going to be different for every problem. I guess you do have to memorize that what a convection boundary condition looks like, and what a conduction boundary condition looks like, or right? So you should know what these look like. But the good news is they're all just first law energy balances, right, on the surface of the system, right? Where did I put it? It's in one of these multiple choice questions. So they're all, you take a control surface here. So all these equations come from, and maybe it looks a little bit intimidating, right? But all of this, what this is, the convection, is you drew a control surface on the edge of the wall here, and you said the conduction going in is equal to the convection going out. So I guess you do have to memorize that in the way that we need to know how to do Module 1 type questions, right? I suppose that you do need to know that if it says a surface is adiabatic or insulated, then that means that the derivative of temperature there is equal to 0. Or if there's a constant heat flux, then that means that, so this is a first law balance. So this says all the heat that goes into the surface is equal to the conduction that comes out the other side of the surface. So this is also a energy balance on a control surface that's kind of the skin of this surface. So you do have to know it. How you choose to know it is up to you. I always hated memorizing things because I think I'm just not that good at it. So I guess I always tried to understand where things came from. So hopefully by understanding that these come from sort of a surface energy balance, you would be able to just figure out what these were. But if that doesn't work, then I would suggest memorizing these things. I will see. I should have a copy of the exam sheet here. And I don't know that it's... I'm just looking at it quickly here. Like I said, when I was going through this, I didn't always see what was on this sheet. So I would just derive something like that if I had it, just, and it's kind of, like I said, it's this module 1 type question. So I don't see those boundary conditions listed here. So I think you do have to know how to get them or know what they are. Are there other questions about this problem?
Nope, that's it. Thank you.
You're welcome. So our next question is not about steak, right? In the pandemic here, all we get is hot dogs. So it's halftime. I guess that this was probably done somewhere near the Super Bowl, maybe. And you are debating whether you have time before the second half to cook a hot dog, you're given some properties, in boiling water, which for some reason is your favorite cooking method, maybe because it's got uniform convection and it makes sense as a heat transfer problem question. The hot dog has a diameter that's given and a length that's given. And because you're taking it out of the fridge, it has an initial temperature of about 5 degrees Celsius. And then you just drop it right in the boiling water. Estimate the time it will take for the hot dog to reach at least 70 degrees everywhere, assuming the convection coefficient is 200 watts per meter squared Kelvin. In part B, says a fellow engineer proposed boiling the water at a faster rate by doubling the heat rate entering the cooking pot, which in turn would double the convection coefficient. So what happens if we double H? How much faster will the cooking approach take? And you got to sort of think. So sometimes this is kind of like, just like vehicle design. You can design a car that's got more power, right? But the trade-off is that you get worse fuel efficiency, right? So here, right? Yeah, maybe you're going to cook the hot dog faster, but how much more energy did you use, right? And it doesn't make sense to do that. Right? So that's obviously subjective, but I mean, you write down a sentence, right? So here I drew out the problem. So I have a picture of a hot dog here with convection coming in. And we're asked first to find the time that it's going to take to get to 70 degrees everywhere. So here we're going to, again, assume 1D conduction. At least initially, it could be, if it's lumped, maybe that there's, no conduction. But I'm going to say that there's 1D conduction for now. That there's constant material properties. Right? It's pretty homogeneous, right? So if you, you get your Shopsy's Red Hots or whatever, then, it's pretty blended up in there, pretty uniform. We're going to have a uniform heat transfer coefficient. Might be Schneider's Red Hots, I guess, right? Temperature is initially uniform. Radiation can be neglected. And the time is unknown, right? So our kind of flow chart maybe breaks down a little bit here because we don't know the time, so we can't calculate the Fourier number, right? Because time is in the Fourier number. So we're going to assume, if it comes to that the Fourier number is big enough that that first term approximation is okay. So I guess I kind of know that, right? Because that's sort of the problem, right? Is that if the hot dog is at least 70 degrees everywhere, that means it's at least 70 degrees at the center, which means that it's not 5 degrees anymore. So the center of the hot dog knows that it's being heated because it's gone up by 65 degrees. So find the time, or estimate the time that it'll take for that to happen. So here I got to go through my convection flow chart, right? Again, I'm always sort of hoping for a lumped analysis because I think that it's just a little bit easier, right? So I have some information. I'm going to calculate my BO number. Now, we do have to remember that the characteristic lengths are different for BO numbers in a lumped analysis and a first term approximation, right? So here my characteristic dimension is volume over area. So I put that in. Again, I like to actually write out the equations because a bunch of stuff's going to cancel out. And this is going to be h times r divided by 2, all divided by k. So I put this in, and I get a pretty big BO number, definitely bigger than 0.1, so I know it's not lumped. Right? So if it's not lumped, and I know it can't be semi-infinite because the center of the hot dog knows that it's being cooked if I'm doing this right, so it's got to be first term approximation. Right? But I got to recalculate the BO number here because my characteristic length changed. It used to be r over 2, which came from volume divided by area, but now it's LC, which is the distance from my adiabatic line, in this case, right? That line goes down the center of the hot dog to the surface of the hot dog, right? So it's just the radius of the hot dog. So now my BO number is twice as big as it would have been for a lumped analysis. And I see that the BO number for the first term approximation is 3. So now I have a cylinder, and its minimum temperature, because I'm heating it from the outside, has to be at R is equal to 0, right? So the temperature there is given by theta star naught, right? So here I know, I looked it up on the equation sheet, that theta star naught is equal to C1 times E to the negative zeta 1 squared times the Fourier number, right? Which is easier to write down than it is to say. But what I'm trying to really solve for here, because I want the time, right? So to get the time, I need the Fourier number. So I got to isolate the Fourier number, right? So I divided, first I divided theta star by C1, right? So I divided both sides of the equation by C1. And then I take the natural log of both sides. And then I divide both sides by negative zeta 1 squared, right? And this is what I get. So first I'm just going to solve for the Fourier number. To do that, I need to know theta naught squared. So this is going to be the temperature at the center of the hot dog at any given time minus T infinity divided by T naught, my initial temperature, minus T infinity, right? So now the temperature at whatever time that I'm trying to find is 70 degrees. So I can put that in, and I see that my theta naught star is equal to 0.316. Right? So now I need to find C1 and zeta 1. So I have to remember that I know the BO number over here, and it's a different BO number. So I would think if I was grading this problem, so I wasn't teaching the class in this semester, but I think that it would have been a very common mistake to keep this BO number at 1.5 and not recalculate with the different characteristic length. So now I go to my table, which would have been provided. So it's not on the sort of standard equation sheet, but if you need to do this, we will provide you with a table. We might provide you with the table even if you don't need to do this, right? So here you see the BO number. You look for the cylinder part, right? So here I snipped it out here, but this is for infinite cylinders. I can find zeta 1 and C1. I put those into my equation, and I see that my Fourier number is just under 0.5. So that's greater than 0.2, which is good. I think that, like I said, just physically, I know that it has to be greater than 0.2. I know that this isn't a semi-infinite problem, but it's nice to see that my math backs that up, right? So that gives me more confidence in my math when I'm finding here that it's saying that the first term approximation is a reasonable thing to do. So now I know the Fourier number is 0.47, but I also know the definition of the Fourier number is alpha times t divided by r squared. So I can isolate this for t, and I know that alpha is k divided by rho Cp. I put all of that into my equation, and I get that the time is 308.5 seconds. So that's good. I could convert this into minutes if I wanted to, right? But it just asked me for the time. It didn't specify the minutes, right? So now I'm into part B, right? So here we're jacking up the heat rate, and we're saying how much faster will it cook and what's the energy difference, right? So first I'm going to answer how much faster is my hot dog going to cook if I do this. So here I'm doubling my heat transfer coefficient, which means that I'm doubling my bond number, or my BO number, I'm sorry, for lumped capacitance, right? So here that this is 6, right? So this is not true anymore, right? So now my BO number, actually, I guess here for the lumped capacitance, it would be 3, right? Because here the lumped capacitance, the characteristic dimension isn't R, right? It's still going to be bigger than 0.1, but this is actually a mistake here, where this is the BO number for the first term approximation that I'm calculating, because my characteristic dimension is R, right? Instead of R over 2. So now we do the same analysis with the BO number equal to 6, right? We just go back and we solve for time, but we have different values of zeta 1 and C1. So when we put those in, we get a different Fourier number, which is still bigger than 0.2. And then when we use that different Fourier number to isolate for our time, we get 243 seconds. Right? So I think before it was around 300 seconds. Now it's around 240 seconds. So we saved a minute. Right? So it's about a minute faster, or 65 seconds faster. But there's no free lunch, right? Even if it's hot dogs. So we do have to see how much extra energy do we consume, right? So what we want to do is we find the total energy. So the total energy is going to be our heat rate multiplied by the time that we apply our heat rate for, right? So in case A, I have 1 heat rate times 1 times the time that I calculated first. And in case B, I have a new heat rate, which is twice as big because I doubled the heat transfer coefficient, multiplied by a different time, right? So I could calculate the heat rate here. I could say H times A times delta T. I think I'm given enough information to do that, but I don't want to, right? I'd have to go in and do the first term approximation and find what the surface temperature is. I don't want to do any of that, but I know that Q is going to be the same in both of these cases, or at least close to the same. Right? So I'm going to cancel those out. Right? So now I have times for part A and part B, and I get 0.63. So the energy used in part A was just about 2/3 of the energy used in part B. If I take the reciprocal, then I can see that the energy used in part B is about 60% bigger than the energy used in part A. So option B is good. It reduces the time by a minute, but then the downside of that is it uses almost 60% more energy. So it's a trade-off, like many things in engineering. So you do have to say, how much is that extra time worth to you? So, you know, sorry, no, you can't watch Baby Beluga. So what happens here is that, you know, you just have to, you put a price on how much that minute is worth to you, right? And that price is in dollars and cents because you're using more energy, but it's also in terms of environmental impact because that energy is coming from somewhere. So that's the end of our second problem. Does anybody have questions about this problem?
Daddy. Can you watch Daddy? Can you watch?
Here, I'll mute myself one sec.
Can you watch Daddy? Can you watch Daddy Butterfly?
So, anybody have questions about how we did this problem? Or about the course in general?
I have a question, actually.
Pardon me?
Yeah, I was struggling with the practice, with practicing like the BI number versus the new. Comparing lumped capacitance.
So there's two different, the BO number always looks kind of the same. Here, let me come back here. The general structure of that equation is always the same, where it's, here, I'm just trying to find the, it's always going to be some effective heat transfer coefficient multiplied by some characteristic length divided by K. Now, the difference is, this is a very common error that people make, is that the characteristic length is different for lumped capacitance versus the first term approximation. So in lumped capacitance, that characteristic length is the volume of whatever your material is divided by the surface area that's exposed to the heat transfer. In the first term approximation, the characteristic length is going to be the length from wherever your adiabatic or symmetry line is to the surface where the heat is being transferred. So we have to kind of make sure that we're using the right characteristic length. Just like when you do internal convection versus external convection, the way that you calculate the Reynolds number is different, because the characteristic Reynolds number for a plate is the length along that plate, but the characteristic length for Reynolds number when you're using internal convection is going to be the diameter or the hydraulic diameter. So whenever you're calculating a dimensionless parameter, you have to know what the right characteristic length is.
Okay, gotcha. I understand now. Thanks.
You're welcome. Any other questions about either the exam or sort of, I guess, information about our exam? All right. Well, thank you very much, everyone. I will see you again on Thursday, where we'll go over the third exam. Thanks very much.